Hello. This video includes information on enthalpy of formation and Hess's law.
So now we're going to talk about what's called standard states, kind of building on this whole enthalpy concept. So when we talk about standard states, okay, they are the commonly accepted set of conditions used to compare things. And we look at them in terms of 1 bar of pressure and 1 molar solutions. Commonly accepted temperatures are 25 degrees Celsius and 298.15 K. And again, we're going to deal with commonly reported, as opposed to what's written here, as a little bit less than 1 bar, and talk about it in terms of ATM. And when we talk about standard state enthalpy values, meaning that we're looking at reactants and products at standard states, we just add this little 0 up here, this not sign. And that just symbolizes that we're looking at standard state values. And it tells us the temperature down here as a subscript. So we're going to talk about what's called the standard enthalpy of formation values. So our symbol is delta H. Okay, that's our change in enthalpy, internal energy. The not sign up here means we're at standard conditions, and the subscript F just means we're looking at the enthalpy of formation. And it's essentially the energy that's associated with the formation of 1 mole of a pure substance from its elements. And the elements are going to be in their most stable states under standard conditions. So if we were to look at the formation of carbon dioxide from its elements, carbon dioxide is formed from carbon and oxygen. Okay, carbon is a solid in its standard state. Oxygen is diatomic, and it's a gas at its standard state. So this would be considered to be the equation for the formation of carbon dioxide from its elements. And you can look up the enthalpy of formation for carbon dioxide on a table, and it tells you that that value is negative 393.5 kilojoules of energy. That means for every mole of carbon dioxide that's formed from its elements, this amount of energy is given off. So if we were to look here, we have nitrogen gas, diatomic and gas, that's the standard state, plus oxygen gas, again, diatomic in its gaseous state, to form nitrogen dioxide. Now, by definition, the standard enthalpy of formation values deal with 1 mole of product. So we have to put a 1 here. This would really be balanced with a 1, a 2, and a 2. But then this number here isn't a 1, and it has to be a 1. So we just divide everything by 2. That's why this equation looks the way it does. The product, the compound that we're forming from its elements, always has to be in terms of 1 mole. And the value for every mole of nitrogen dioxide that's formed from its elements, 33.2 kilojoules of energy have to be absorbed. And when we look at these values, they range from really exothermic, meaning lots of energy is released when that compound is formed, to really endothermic, meaning lots of energy has to be absorbed in order to form that compound. And again, the standard enthalpy of formation for the elements are always going to equal 0. So carbon is 0. Okay, why? Because it's not a compound. It's not being formed from its elements. It's an element itself. O2 would have an enthalpy of formation value of 0 because it's not a compound. It's an element in its standard state. Okay, and nitrogen would be 0 for its enthalpy of formation value. And you can look these values up on a table, and we're going to use those values in a couple of different kinds of problems. So we're going to do a couple of practice problems. We'll do the first one together, and then we'll see if you can do the second one on your own. So we have this compound here. It doesn't really matter what it is, but C2H5O, C2H5. And we want to write the equation for the formation of this compound from its elements in its standard state. So we have to think about what elements is this compound going to be formed from? Well, it's going to be formed from carbon, it's going to be formed from hydrogen, and it's going to be formed from oxygen. And we have to think about what carbon, hydrogen, and oxygen are in standard states. Carbon is a solid, hydrogen is a gas and it's diatomic, and oxygen is a gas and it's diatomic. So when we go to write down the heat of formation equation, we would have carbon plus hydrogen gas plus oxygen gas forms this compound. And then we need to balance it. There's 2 plus 2, there's 4 carbons, so we need to put a 4 here. There is 5 plus 5, there's 10 hydrogens, so we need to put a 5 here. And then that should not be a 12. Not sure this one's balanced. That one is not balanced. That's unfortunate. Okay, so we'll look at the second one because the first one is not balanced actually. This is sodium sulfate. So it's going to be formed from sodium, sulfur, and oxygen. Okay, sodium is elemental. We'll put our S in there. Sulfur is actually S8 in its standard state. We looked at that at the beginning of the year. We don't necessarily have to put rhombic in there. We just put that as a solid. And oxygen's diatomic and it's a gas. To produce sodium sulfate, there should be an S here. So we've got 2 sodiums, 2 sodiums. We've got 1 sulfur, so this is going to have to be 1/8 of this free element. And then we've got 4 oxygens, so 4 oxygens. The key to this is that the product, the compound that we're forming from its elements, has to be a 1. I apologize that this first one is not balanced. We can use the standard enthalpy of formations to calculate the enthalpy for a reaction. So now we're going to combine 2 things together. How do we do that? The enthalpy change for a reaction equals the sum of, that's what this sigma sign is here, the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation for our reactants. Now, the N's that are in here are the number of moles that are present in the equation. And the reason that we have to incorporate that in there is because the values that are on a standard enthalpy of formation table are per 1 mole of a compound that's formed from its elements. And there may be more than 1 mole in the balanced equation. The H of formation is the standard enthalpy of formation values, which you can look up on a table. And again, just noting that pure elements in their standard state have an enthalpy of formation value of 0 because they're not compounds being formed from their elements, they're elements themselves. So this is the equation that we're going to be working with. It's the sum of the products minus the sum of the reactants. So here's a table. Let's just look at this table for a second. It lists several compounds, and it gives us the enthalpy of formation value for each of those compounds. So if nitrogen gas, 1 mole of nitrogen gas, or ammonia gas is formed from its elements, 46 kilojoules of energy would be released. If 1 mole of nitrogen dioxide was formed from its elements, 34 kilojoules of energy would be absorbed. So that's what these values are, and we can look them up right on a table. Okay, every textbook has an enthalpy of formation table in it. So we're going to use this information to come up with the enthalpy of reaction for this reaction. Now, we're not forming 1 mole of a compound from its elements this time. So what we're going to be doing is taking the sum of the products and subtract the sum of the reactants. And we're going to be multiplying all of these numbers by the coefficient in the balanced equation. Because as an example, the value that we're giving for ammonia, this -46, is kilojoules per 1 mole of ammonia. And in this reaction, we have 4 moles. So we're going to have to multiply this number by 4. Now, oxygen isn't on this table. And we just have to know that oxygen is a free element and its value is 0. It's not going to show up on tables. It's just something we're going to need to know. So we're going to start by writing our equation. So the enthalpy of reaction for this reaction is the sum of the enthalpy of formations of our products minus the sum of the enthalpy of formation for our reactants. So let's start with the product side first. We're going to take 4 times the value for nitrogen dioxide plus 6 times the value for water. And that would give us the sum of the products. Then we're going to look at the reactants. We're going to take 4 times ammonia plus 7 times 0, which we really don't have to write. And then we just do our math on this. Now notice that the moles of nitrogen dioxide are going to cancel out, and the moles of water are going to cancel out, and the moles of ammonia are going to cancel out. That's why we're multiplying by the coefficients in the balanced equation. And when we plug all that into our calculator, we're going to get negative 1,396 kilojoules per mole of reaction. So once we calculate this value, we could go up and do a stoichiometry problem like we did in our previous slides. We're just kind of starting from an earlier starting point. So let's try another one. Okay, we want to calculate the enthalpy of reaction for this reaction here. Now, C6H12O6 glucose is not on this table. This is a very abbreviated table, so I gave you the value for C6H12O6 up here in the context of the question. So we're going to take carbon dioxide and water, and we're going to produce glucose and oxygen. That might look familiar. It's the general equation for photosynthesis. And we want to calculate the energy associated with that reaction. So you're going to take the sum of the products, so that's over here, and then you're going to subtract the sum of the reactants, that's over here, making sure that you're taking the values and multiplying them by the coefficient in the balanced equation, and see what you get for the enthalpy of reaction for photosynthesis. And I know it'll take you a couple minutes, and you got to be kind of careful not to drop numbers as you do it. So I would really be careful with showing your work and not kind of shortcutting stuff. And when you're done, let's get a couple of answers in the chat, see how we did, and then we'll put up the answer. All right, so when we look at the product side, when we want the sum of the products, again, glucose wasn't on the table, so I put it in the context of the question. And there's a 1 for the coefficient. So 1 times negative 1275, that's the sum of the products. Again, remember that oxygen 0, we could put in here plus 6 times 0, but it's 0, so we don't really do that. We're going to take the sum of the reactants next. And I did just break this up. We'll break this up to make it a little bit easier for you to see how you calculate this. You can just do it all on one line. So we've got 6 times carbon dioxide plus 6 times water. And you do have to be careful. The table that I gave you was a very abbreviated table. If you look at tables like in appendices of textbooks, oftentimes they'll have things like water in the gaseous state and the liquid state, and you have to make sure you're using the right states. But that really wasn't an issue with this here. So we've got carbon dioxide times 6 plus water times 6. That's the sum of the reactants. And then we add those values together and we get 2,805 kilojoules per mole. Now the value is positive because you want to take the products minus the reactants, not the reactants minus the product. So if you got a negative, that would be why that is. So, make yourself a little note. And also think about what photosynthesis is. I kind of pulled that in there as a concept you've hopefully learned in a biology class, that plants carry out photosynthesis by absorbing energy. And this is the amount of energy that's absorbed per mole of glucose that's formed during photosynthesis. And what we're going to do now is we're going to start talking about Hess's law. So we dealt with the enthalpy of formation values and how we can write an enthalpy of formation equation and how we can look up the value on a table, and we can do some stoichiometry with it. And then we use those enthalpy of formation values to figure out the enthalpy for a reaction by taking the sum of the products minus the sum of the reactants. The next step, that's just building on, is called Hess's law. And since enthalpy is a state function, it doesn't matter how we get from the beginning to the end point. It's just the difference between what did we start with and what did we end with. So as an example, if we were to take nitrogen gas and oxygen gas and produce nitrogen dioxide, the way that this reaction is written, 68 kilojoules of energy would be required for 1 mole of this reaction. So 1 mole of nitrogen, 68 kilojoules, 2 moles of oxygen, 68 kilojoules, 2 moles of nitrogen dioxide, 68 kilojoules. But this reaction can actually be carried out in 2 distinct steps. So nitrogen gas could react with oxygen gas to produce nitrogen monoxide, and that requires 180 kilojoules of energy. And then that nitrogen monoxide that was produced in the first step could react with oxygen and produce nitrogen dioxide, which gives off 112 kilojoules of energy. Now, the nitrogen monoxide is produced in the first step and it's consumed in the second step. So we can add this reaction up and just cancel the nitrogen monoxides out. And Hess's law states that if we add up 2 reactions to get an overall reaction, the energy for that overall reaction is the sum of the individual steps. So the nitrogen gas plus 2 oxygen gives us 2 nitrogen dioxide. I'm adding up these 2 reactions, canceling out what was produced in the first step and what was consumed in the second step. The energy is the sum of the individual steps. Now, look at the energy for the reaction if it goes in 1 step versus the energy that's required in order for us to carry out this reaction in 2 steps. They're exactly the same number. Because when we look at enthalpy values are state functions. So this is kind of a graphical representation of the numbers we had here. So if we were to start with nitrogen and oxygen gas, they would react together and they require energy. They require 180 kilojoules of energy. But if that nitrogen that's produced reacts with oxygen, to produce nitrogen dioxide, we're going to get back 112 kilojoules of energy. The net is 68 kilojoules of energy. It doesn't matter that we started here and went up here and then came back down here. We're really concerned with just the net change because it's a state function. Just like if we were to just go directly from nitrogen and oxygen to nitrogen dioxide, our value would be the same. So this is the idea about Hess's law. So let's look at another problem. And they'll kind of just get a little bit harder as we go along. So we have iron and oxygen reacting to form iron 2 oxide. And we're told that this reaction has an H value, a heat value of negative 544 kilojoules of energy. And we're given the second reaction where iron reacts with chlorine to produce iron 2 chloride. And that releases 341 kilojoules of energy. We want to use this information that we're given to figure out what's the standard enthalpy change for this reaction. So we're going to need to manipulate these two equations so that when we add them up, they add up to this overall equation. And remember that if we have to multiply a reaction by some coefficient, we have to multiply the energy by that value. And if we have to flip a reaction around, the sign on the enthalpy value changes from positive to negative or negative to positive. So the way we would want to work this out is we want to end up with iron 2 oxide on the product side. And it's on the product side in what we're given. But we're going to want to end up with iron 2 chloride on the reactant side when we're all done. And it's given to us on the product side in the second reaction. So that means we're going to need to flip this second reaction around in order to get that iron 2 chloride onto the side we need it on. So we'll leave the first reaction the way it is. We're going to flip the second reaction around. And again, the reason we're going to flip it around is so that this FeCl2 ends up on the reactant side. And we don't want to end up with one FeCl2. We want to end up with 2 FeCl2. So we're going to have to multiply that second reaction by 2. So that means we're going to have to do the same change to the H value. We're going to have to change the sign because we're flipping the equation. And we're going to have to multiply that value by 2 because we need to multiply the equation by 2. So this negative 341 kilojoules, the sign gets flipped, we multiply it by 2, and that's where that 683.6 kilojoules comes from. Now, if we look at these two reactions, we've manipulated them from the given equation. 2Fe is on the reactant side here, and it's on the product side here. That's going to cancel out. And that's the only thing that cancels out. So Hess's law says if we add up these two reactions and they give us the reaction we're looking for, we can add up the energies and it's going to give us the energy for what we're looking for. So we've got 2 FeCl2 plus O2 yields 2 FeO plus 2 Cl2. So we manipulated these equations so they add up to what we're looking for. We're just going to add these numbers up, and that's going to tell us the energy associated with this reaction. And again, once we know this number, we could go back and do a stoichiometry problem on that. So let's look at another example of a Hess's law problem. Okay, this time we're told that N2 plus 2O2 yields 2NO2, and that's positive 66.4. And the nitrogen monoxide plus oxygen to produce nitrogen dioxide is negative 114.1 kilojoules. And we want to calculate the standard enthalpy of formation for nitrogen monoxide. So the standard enthalpy of formation of NO means we're forming this compound from its elements. So we want nitrogen plus oxygen to produce nitrogen monoxide. We don't know that value, but we want to calculate it from the information we were given. So this is what we want to calculate. Okay, 1 mole of nitrogen monoxide from its elements. So we're going to have to manipulate these equations. All right, well, we want nitrogen to end up on the reactant side. It's in the first reaction, and it's on the reactant side. So we're not going to need to flip this first equation, but we are going to have to divide it by 2 in order to get this 1/2 we're looking for. We want to end up with NO on the product side, and it's in the second reaction, but it's written on the reactant side. That means we're going to need to flip this second reaction around to get NO onto the product side. And we don't want 2 moles of NO, we only want 1 mole of NO. So we're going to have to not only flip this reaction, but divide it by 2. So we look at what we want to find, and we have to figure out what are we going to do to the given equations to get what we're looking for. And then whatever we do to these equations, we have to do exactly the same thing to our delta H values. So we're going to leave this reaction the way it is, but we're going to divide all the coefficients by 2, which means we have to divide the energy by 2. We're going to flip the second reaction around, and we're going to divide by 2. So that means we need to change the sign on delta H from negative to positive, and we need to divide it by 2. So that's where that 57.05 comes from. So now Hess's law states that if we add up these reactions, it's going to give us the energy for the overall reaction we're looking for. So we have 1 O2 here. We have 1/2 an O2 here. So our net is 1/2 O2 on the reactant side. So we have 1/2 N2 plus 1/2 O2. Our NO2s cancel out, and we have 1 NO. That's the reaction we're looking for. We add these values up, and that gives us the energy for the reaction. We want to figure out the delta H for this reaction. So we've got methane reacting with ammonia to produce hydrogen cyanide gas and hydrogen gas, given this information. So what we have to do is look at what we're given and decide what we need to do to each of these given reactions so that when we add them up, they add up to the overall reaction. And whatever changes we do to the given reactions, we have to do the same thing to the delta H values. And then we can add them up, and that'll give us our value. So I like to kind of work from what I want to from what I'm given. So I want to end up with CH4 on the reactant side. It's here in the second reaction. Think about what you have to do to this reaction to get CH4 where you want it to be. Sometimes you don't have to do anything, but it's on the product side and we want it on the reactant side. Think about that. We want ammonia on the reactant side overall. It's in the first reaction, but it's on the product side. That's not where we want it. So we're going to have to do something to this reaction. Plus, we want to end up with 1 mole of ammonia. And we have 2 moles of ammonia in what we were given. Okay, then we look at HCN. We want it on the product side. Well, it's in the third reaction. and it's on the product side, great. I don't have to flip my reaction. But I do only want 1 mole in my final reaction, and I have 2 moles in what I'm given. So see if you can figure out how you want to manipulate those equations so they add up to get the overall equation. And then once you do that, whatever you do to the equations that are given, do the same thing to the energy and then add up the energies. And we can do this because delta H is a state function. It doesn't matter whether we just go from reactants to products or we do 3 separate reactions. We're going to get the same overall result. All right, so we're going to take this first reaction. We're going to flip it around and we're going to divide it by 2. We're going to take the second reaction and we're going to flip it around. So we're just going to change the sign. And in the third reaction, we're not going to flip it, but we do have to divide it by 2. And again, whatever we do to the reaction, we have to do to the energy. So that's going to leave us with CH4 plus NH3, the 1/2 H2, and the 3/2 H2 cancel out, and we end up with 3 H2 on the product side. And the carbon on the product side and the carbon on the reactant side cancels out, so it doesn't end up in the overall reaction. We get HCN, and we already looked at the H3. So adding these reactions up does in fact give us the reaction that we're looking for. So we just add up these energies and that'll give us the overall energy that we're looking for.